Our next speaker today is Dr. Srdjan Lukic, also from NC State. Dr. Lukic is an associate professor with the Department of Electrical and Computer Engineering. His research interests include design and control of power, electronic converters, and electromagnetic energy conversion, with an application to wireless power transfer, energy storage systems, and electric automotive systems. He served as a distinguished lecturer with the IEEE Vehicular Technology Society from 2011 through 2015. And Dr. Lukic is going to talk about his wide bandgap enabled medium voltage EV fast charger. Dr. Lukic.
Good afternoon, everyone. I'll talk about our wide bandgap medium voltage EV fast charger, and I want to acknowledge. Let's see, my collaborators here, Dr. Srdjan and Dr. Yu, as well as our graduate students and our undergraduate students. So, in this presentation, I'll give an overview of the motivation for a project working on medium voltage fast chargers, then what are the actual specifications of the prototype that's in development, and then I'll talk about some salient design points for the system, and close off with our plans for the future. So looking at the state of the art for fast chargers, you can see that the products that are currently on the market are typically rated at 50 kilowatts, and they connect to a three-phase 208 or 480 volt AC connection. The efficiency is somewhere in the mid-90s, not including the step-down transformer that takes the medium voltage distribution voltage down to the low voltage. The volume is somewhere above 700 liters and above 700 pounds weight. The exception is the Tesla supercharger that's rated at 120 kilowatts and is also connected to three-phase power supply, low voltage, but has an efficiency of about 92%. So looking in the future for fast chargers, we're expecting the capacities to be well above 50 kilowatts in the future. Tesla already has the 125 kilowatt unit out in the market. In Europe, 150 kilowatt chargers have been demonstrated, and with GM and others coming out with vehicles that have battery capacities over 60 kilowatts, we are expecting higher capacity chargers as well. In fact, both CHAdeMO and CHAdeMO standards are calling for 150 kilowatt or higher capacities in their standards, with a long-term goal of 350 kilowatts or higher. So let's look at why we're proposing to go with medium voltage fast chargers. Looking at the state of the art, which is 50 kilowatts, and that's what we're focusing on at this point. The 50 kilowatt fast charger requires a dedicated step-down transformer, or essentially requires a step-down transformer that has a substantial weight and volume, and a dedicated concrete pad. Typically requires a dedicated concrete pad. Then, as I mentioned, the charger itself has a significant volume and weight in itself. And of course, when we cascade these two components, the efficiency suffers, since we have to consider both the efficiency of the transformer and the charger itself, bringing us somewhere in the low 90s for the overall system efficiency. What we're proposing is to replace these two components with a single wide bandgap medium voltage fast charger that connects directly to the medium voltage line, with a volume goal of 100 liters and a mass of 60 kilograms. Peak efficiency should exceed 95%, and our goal is 96.5 or higher. Again, the idea is to have a system of similar cost, but to save substantially in terms of operating costs and the efficiency is higher, and also to save substantially in terms of the installation costs, especially in seismically active areas where concrete pad pours have to be seismically constrained. So going on with our project goals, what we're trying to develop is a 50 kilowatt charger at this point, connecting directly to the medium voltage line. So the rating is 50 kilowatts connected to 2.4 kV, delivering 400 volts DC nominal to vehicle. Efficiency over 95%, high power quality, 10x size reduction, and 4x weight reduction, with a simple installation without a step-down transformer. We're hoping this can help us establish a building block for medium voltage rectifiers, both through the lessons learned in building medium voltage rectifiers, but also since the system is modular, as I'll mention in a minute, we can actually scale to higher voltages and higher power levels. And finally, of course, our goal is to go from TRL4 to TRL7 and hopefully beyond. So this slide summarizes our design process for the system. We started with a topology selection, component selection. Our goal, of course, was to use off-the-shelf silicon carbide devices. Since we wanted something that could be manufacturable fairly quickly. Then we did our initial simulations to understand the control and the expected efficiency, verified the controller code, built a breadboard prototype, and based on the lesson learned, improved our simulation fidelity to get a better efficiency estimate. We redesigned components based on these lessons learned, improved our controller code further, and then finally constructed the entire system. We're in the process of system testing, and finally now we're doing further optimization with main goals of safety. So we're looking at protection approaches, and of course we're trying to improve our efficiency. So what I'll do in the remainder of the presentation is really talk about some salient points about the design, and close out with our plans for the future. So this is the actual topology we selected. We have a low-frequency full-bridge diode rectifier, followed by a multi-cell boost used for the power factor correction. Then we have a DC bus, and then a DC to DC converter. To deal with the high input voltage, we series connect three such modules. And to deal with the low voltage and high power on the output side, we connect all the modules in parallel on the output side. And of course, we rely on the high frequency transformer for isolation. So as I mentioned with this design, since the system is modular, with the current prototype, we have the system shown here, but we can stack multiple modules to reach a higher input voltage level and higher power. And then if we go to higher voltage devices down the line, we can go to still higher power levels and even three-phase designs if we're looking at the 350 kilowatt type system where a single-phase grid connection would not suffice. Moving on, this is the design procedure that we followed, showing the main hardware prototypes that were built over the past first year. This shows our breadboard module prototype based on some initial device selections. Based on the lessons learned here, we essentially redesigned almost every component of the system. And this is the final fast charger prototype that shows this modular design where we sacrifice the power density a little bit for manufacturability, where each module is essentially a building block on its own. Here are the device selections or the devices that we're actually using in the system. We have, as I mentioned, a low-frequency full-bridge rectifier here. We're actually using silicon devices here, since for the low frequency and the high voltage, they're both cost-effective and even more efficient given what's out in the market today. And then all the other components we're using are, of course, silicon carbide. We're using the Cree or Wolf Speed dies in microsemi packages for the MOSFETs you see here, and then using again the Cree dies and microsemi packages for the die. All the devices come in packages isolated to 5 kilovolts, so we can actually mount all of these components directly on the heatsink without worrying about any voltage issues there. In terms of the controller design, we have a simple control scheme where we have a power factor correction stage that controls the cascaded boosts that are also interleaved. We have a balancing loop, making sure that all the capacitance, all the voltages across the capacitors are balanced. And then finally, on the output stage, we have a simple PI control to control the output voltage or output current, depending on if the vehicle battery is in the constant current or constant voltage charge mode. In this BP, we've actually improved the power factor correction control to use predictive control, and we're getting substantially better results in terms of PhD and the performance around the zero crossing of the current. Here's the actual complete system that is constructed, and I'll discuss each of the components in a little more detail in the following slide. Here we show our stage, or the stage that combines the boost and the NPC of the DC to DC. They're all mounted on the same heatsink, and the DC link capacitor is actually mounted below the heatsink shown here. Over here you see the bus bar that connects the capacitor to the PCB bus bar that actually connects all the MOSFETs and diodes. We're using off-the-shelf gate drives at this point. We've actually had some issues with these gate drives, and we're in the process of redesigning our own gate drives to both improve the power density, but also, more importantly, to improve performance. We're using fiber optic communication to trigger the switches, and we're using a custom designed voltage sensor with fiber optic communication to measure the DC, the capacitor voltage. Here's the bus bar design. We try to make it as symmetric as possible, of course. And here you can see the MPC modules, the boost stage modules, and the diodes for the MPC and boost stage. Moving on, we have improved, we have the another heatsink that houses the rectifier stage and the RCD snubber that we're using to contain the ringing between the two inductors with diode serving as the capacitors. We have the ringing on the parasitic capacitor of the diodes that's controlled by this RCD snubber. We went through a couple of iterations on the inductor designs to improve power density and efficiency as shown here. We've also designed a custom crowbar circuit shown. The crowbar circuit is housed here below the transformer. The crowbar circuit measures the DC link capacitor using this voltage divider shown here that then triggers the SCR device when the DC link capacitor is too high. The inrush resistor limits the inrush current, and our protection scheme triggers with milliseconds or below that after the inrush current is detected. So the inrush resistors are shown here. They're sized to sustain the inrush current for a short period of time to minimize the system size. The high-frequency transformer is shown here. We've tested its isolation up to 15 kilovolts. Of course, the limitation is the equipment we had available. So we can guarantee that the transformer operates well until 15 kilovolts. We've optimized the leakage inductance of the transformer to guarantee soft switching on the outer MPC switches at currents about 20 amps. And lighter load, we would actually have hard switching on the MPC switches, but that's acceptable at this point. We've obviously hand-wound these transformers, but the leakage inductances are fairly close to each other, as shown here. The soft switching border was actually tested experimentally and also validated in simulations, or I should say the other way around. So moving on, sensing, of course, is a major concern. On the input side, we have used these LEM sensors to measure the high voltage input, and we use a high bandwidth current sensor to measure the current through the input inductor. On the output side, again, we're using LEM sensors. And then to measure the capacitor voltages, we've designed a custom voltage sensor. The voltage sensor uses the gauge rod power supply to power up the sensor. We're measuring the actual capacitor voltages and sending through a single fiber, the information back to our controller. We're using Manchester encoding to be able to use a single sensor to send the information back, or I should say a single fiber to send the information back. Looking at the control board, this is the actual design. We have 3 modules here, one for each of the physical modules of the system, and we're using a TI DSP as shown here. Looking at the system efficiency, we projected a 96.6% efficiency using 25 kilohertz switching at the boost stage and 50 kilohertz for the MPC stage. To improve efficiency further, we want to replace the diodes at the output stage with switches and do synchronous rectification. For the boost stage, we plan to reduce the switching frequency further to reduce these losses further. So we think we can exceed 97% efficiency with these changes. We'll see how high we can get. And here are some experimental results. This shows the efficiency values. This shows the current waveform for the entire system at 25 kilowatt load. We limited our power output to 25 kilowatts because of the limitations of the equipment we have in the lab, and also this was actually the goal in our fourth quarter of the first year. You can see the THD is 4%, a little higher than we wanted, and that's due to this issue or distortion close to zero crossing. That's due to the use of the PI controller that wasn't optimized. Moving on, here are some additional experimental results showing the interleaving and showing the power output. Again, this slide shows the distortion around the zero crossing, and this shows the experimental results for a single module. With the predictive control, you can see the THD is reduced. When we combine the 3 modules and implement the interleaving, we believe it can be well below 2% THD, which will allow us to further reduce the switching frequency of the system. We'll also involve undergrads in our project quite a bit. They've actually helped us design the capacitor bank that you see here below the heatsink. They've actually designed a bus bar that connects the individual capacitors that we're using, and this bus bar that connects to the PCB. They've also developed a CHAdeMO interface between our charger and the vehicle. So the CHAdeMO interface is used to communicate between the vehicle and the charger. This summer, we had undergrads involved. Alex and Tim were working on developing a controller that would ensure that each one of our resistors on the load bank see the same temperature, and what they did is basically they modulated the speed of the fans we have on the ends to ensure that the temperature is the same. So they designed their own PCB. They use the Raspberry Pi. They programmed it to do the work here. And then this year, we're excited about actually involving undergrads in another project. We've seen that the undergrads enjoyed kind of working on small portions of our larger effort, which was the fast charger, but they haven't had a chance to take kind of a system design from beginning to an end, concept to a product. And this year we've tried to do that through the senior design effort. So we're combining some resources in PowerAmerica and Lockheed Martin specifically. They've helped us fund this project. And we're hoping to have students over a year, again, go from an idea, which is to wirelessly charge this all-electric vehicle, so to take that from a concept to a product or to a system that's integrated with the vehicle. Finally, I'll talk a little bit about packaging. This is something we've spent quite a bit of time. Dr. Srdjan, who's really been spearheading a lot of this work on the charger generally, has spent a lot of time on this enclosure. And this is what the final system is going to look like, showing the 3 modules and all the auxiliaries down here with a user interface shown on the, of course, on the panel here. So future efforts, very briefly, protection, of course, is a major issue that we're dealing with right now. Designing a protection scheme for the system that, of course, is related to safety, ensuring that our box is shatterproof. For example, of course, since we're dealing with medium voltage, there's a number of concerns there. We're looking at what kinds of certifications we would need for this system. Beyond that, we're looking at how we can improve the efficiency of the system. Again, we're targeting 97 plus efficiency for the system. We are also optimizing subsystems further, specifically the gate drive, as I mentioned. We're redesigning the gate drive since we had some issues with the off-the-shelf gate drive that was available. And the auxiliary power supply, right now we're using a low-frequency transformer for our auxiliary power supply, which takes a lot of space and volume in our enclosure. And finally, there's a lot of issues that have to be considered with actually demonstrating our charger with the Nissan Leaf that we have available in our lab. So with that, I'll stop and take any questions.
Thank you very much, Dr. Lukic. That was a very good presentation. Again, if you have any questions, please type them into the chat window. And we'll begin. I'm going to get this mouse back. How do I get my mouse back to the regular mouse?
Here.
We'll go down there.
Let's just end the presentation. There.
All right. Sorry about that. Okay. See where that was one of Dr. Bob's questions. Are you going to incorporate the vehicle-to-grid power transfer feature in your project? If yes, what are the best alternatives for the diode rectifiers in your topology?
No, we're not looking at vehicle-to-grid at this point. Yeah, there's a lot of debate if that's a concept that will really take life, but what the current standards at least are calling for is unidirectional power flow. So as the comment itself mentions, we do have diode rectifiers input in. So doing bidirectional power flow would require a change of the topology. Maybe a modular multi-level converter would be an option in that case. But really, we selected this topology to minimize system costs, since, as you saw, we are using relatively small number of silicon carbide devices in the system compared to some of the other topologies out there.
Thanks. And what drove the decision to use the Nissan Leaf for demonstration rather than others, such as a Tesla?
Purely what we had available in the lab. So in the Freedom Lab, we actually have a Nissan Leaf available for research purposes. And also the CHAdeMO standard has been around a little bit longer, so there's a lot of online information in terms of how we can interface with it fairly easily. So that was the main reason. I think down the line, we would like to support other standards like the SAE standard, the combo standard, and others.
Okay. I have a question. Have you found any interest from any of the commercial producers of the fast chargers that you showed in the very beginning in your concept of using wide bandgap devices to get down to the much smaller size? And have you talked to any utilities about whether they see an advantage of being able to connect directly to the three-phase distribution voltage as opposed to having a pad-mounted transformer? So actually two questions.
Yeah, so we did talk to a couple of, one car manufacturer and a couple of the companies that were listed on the first slide that manufacture these chargers. And they are interested in the concept and are following our work. In terms of the utilities, actually, the concept of a medium voltage fast charger was first spearheaded by EPRI, which of course is supported by so there seems to be at least some buy-in from the utility side. One option of actually deploying at least a 50 kilowatt system is to actually pole mount the charger itself, just like you would a pole mounted transformer, and just to bring down the DC line to the vehicle. So there is some interest from the utilities. We had some talks with Duke in terms of what we're doing, but nothing concrete has come out of that just yet.
Okay, thanks. Before we wrap up, are there any more questions from the audience? Okay, hearing none. Thank you all very much for joining us today. We had two very good technical presentations, and as I said, we'll be doing this every month, and our next technical webinar series will be on October 2nd. So please join us again, and have a wonderful day.